Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this class we are going to look at magnetic resonance imaging, specifically the physics of MRI, and in the next video we will look at some of the image acquisition techniques as well as the hardware required for magnetic resonance imaging systems. Okay, so here's the outline. We are going to look at a brief introduction to the origin of magnetization in the sample. We'll understand how the individual spins, so-called spins, interact with the external static electric field. We'll understand terminologies related to transverse and longitudinal magnetization, and then we'll look at the origin of the MR signal, the one that is used for actually putting together the images that you see from an MR scanner. Okay, so microscopic magnetization. Okay. So every nuclei has both charge and the so-called spin angular momentum. Now the spin angular momentum is actually an intrinsic property of the nuclei, and it has no counterpart in classical physics, in the sense that the idea of spin originates from quantum mechanics, but we will not go into the details of how it came about. I just understand that in addition to charge, the nuclei also have this spin property. And this is the property that gives rise to the magnetism. So each nuclei, basically ones with odd atomic number or mass number, they possess something called the spin angular momentum. We denote that by phi. Okay. The spin angular momentum gives rise to magnetic properties. That's the one that that's the one that interacts with the external magnetic field. The microscopic magnetic field has a magnetic moment associated with it that primarily comes from the spin, and that moment vector we denote by mu, which is gamma times phi. This gamma is known as the gyromagnetic ratio, and it can be measured for different type of nuclei. Okay, so the gyromagnetic ratio has units of radians per second per Tesla. Sometimes you will also see this notation, which is nothing but gamma bar, which is gamma by 2 pi. Okay. Now I'm kind of going to abuse notation and use gamma and gamma bar interchangeably, but wherever required, I'll try to mention that, and you can put the appropriate symbol. Again, this class is just to understand some at a qualitative level how MR images are produced, and also understand the mechanisms of contrast. So that's where we are actually headed, right? Okay, so the macroscopic magnetization comes from all these individual spins. So if you can think of a system of spins, right? So basically, if you look at our body, we have a lot of water in our body is mostly water. So there's a lot of hydrogen atoms in there, mostly protons. So they are the overwhelming contribution to the spin, right? So in the absence of any external magnetic field, all these spins are randomly oriented. Okay, so you can think of these spins like a compass needle, right? That's something like this, that are oriented in random directions. Okay, and these randomly oriented spins cancel each other out, leading to a net bulk magnetization or macroscopic magnetization. Okay, but in the presence of a static magnetic field, let's say along the z-axis, so without loss of generality, we can always assume that if we apply a static magnetic field, it will be that the direction of that magnetic field is the z-axis. So the magnetization vector is actually a vector, so is the magnetic field is also a vector, right? And in that case, what happens when there is a static applied magnetic field? There is a preferred orientation of spins, okay, along the direction of the applied field. Okay, and this leads to a net magnetization, which we can write in this form, which is basically the sum of individual nuclear magnetic moments, okay, in a sample. Okay, you can think of this as a vector sum. rather than a scalar sum. Okay, think of it as a vector sum. Now, there is actually an expression for this. So, if you leave the sample, a particular sample, in a static magnetic B0 field long enough, that is for a certain period of time, because it takes time for all the individual magnetic spins to orient along the direction, or in this case, actually, if from the quantum mechanics point of view, the spins generally align either along or opposite to the direction. Okay, that's a possibility, but we won't analyze it that way. We'll get to that analysis later. So right now, it's just that we have an expression for the M0. But what is more important here is that M0 depends on the strength of the applied static magnetic field, which is B0. It also depends on this PD. PD is nothing but the proton density. Proton density. In this case, the proton we are talking about is the hydrogen atom proton. Okay. So basically, which we now have an idea of what the kind of signal that is produced, which the signal produced depends on, actually we will see later that the signal produced depends on M0, which in turn depends on this applied magnetic field as well as the density of protons. Okay. So this magnetization is what is induced by the presence of a static magnetic field. And we are considering a sample, let's say in this case the human body or a piece of tissue. Okay. But this magnetization, it turns out, is just not static. It is actually a function of time, and it need not be homogeneous also, right? In the sense, it's also that spatially dependent. Okay, as at least in NMR experiments, that is what will happen. So this M0 or M, I will call it, will be a function of space as well as time. Okay. Now we'll define one other quantity just for the sake of analysis. See, there is a bulk angular momentum that we can define. So remember that we have for every individual nuclei, we said there is something called a spin angular momentum. So we can also say for the sample itself there is a bulk angular momentum J, and it's related to the magnetization of the sample through this expression, where once again this gamma is the aeromagnetic ratio. Okay. So in this case, now we are like, just to clarify, we are always talking about a sample. When I say sample, it's basically a piece of tissue or a human body in a static magnetic field. Okay. Now, before we analyze, where the signal comes from, just have to keep in mind there are three factors. We'll eventually find out. There are the three factors which contribute to the contrast in an MR image. Okay. The appearance of an MR image is influenced by these three factors. One is called T1. These are relaxation times, T1, T2, and the proton density. Okay. In addition to this, how these contrasts vary, whether the T1 contrast is higher, T2 contrast is higher, or PD is higher, is determined by so-called pulse sequence. Okay, and we will see what that is also in its later slides. The pulse sequence determines which one of these contrasts is kind of contributing more to the image. Okay. All right. So what happens when you apply a static magnetic field? So now we know that there is a spin angular momentum for individual nuclei, and there is also this bulk angular momentum J. And so what happens is that that rate, there is a torque induced, and the torque induced on which depends on the static magnetic field. So now if you have studied some high school physics or 12th standard physics, you have seen that if there is a current carrying loop and you put that in a magnetic field, it experiences a torque. It's very similar to that. The rate of change of angular momentum, which is the torque, which is dJ by dt, this is the torque that you are usually talking about, is basically the cross product of the magnetization and the applied static magnetic field. Okay, this comes from, you must have seen this in plus 1 or plus 2 physics, where you see basic electromagnetism. From there we can write this expression. So it's M cross B, dJ by dt is M cross B. Now why do we need this? Because this actually gives you like the equations of motion, so to speak, of the individual of the magnetization vector itself. Okay. Now, so the J, we know that is the angular momentum vector associated with the magnetization M. So M is gamma J. So you can always substitute there. Okay. And also we know that BT can always be aligned with the positive Z direction. So we will always say BT by B0. Okay. So right now this B0 is a static magnetic field. There is no this particular B0 as it is applied in an MR scanner, is actually quite homogeneous, and it doesn't vary with time. The B0 field, as it's called, which is typically the direction along which we apply it to be Z axis, so that doesn't change. Okay, so then we can always say BT is B0, and we also substitute instead of J, we will substitute M. So why do we do this? Because see, what we want to do when we do MR imaging is we want to map this M. Okay. And this M in terms depends on, we saw it, B0, we also saw it depends on PD, and the other two factors the other two factors that can be controlled, that can be brought to bear on the contrast, is also the T1 and T2 relaxation times. Okay, so all of this are expressed through this M. This is what we are trying to measure, right? And this we want to measure as a function of space and time, and that's why we want to write this equation, this dj by dt, in terms of the magnetization. Okay, now if we solve that differential equation, right, this differential equation, if we solve for the magnetization, remember we can always put m equal to gamma j and substitute here, and when we solve this equation, we see this, we'll get the following solution. Okay, so we won't go into the details of how it's solved, etc. It's a straightforward ODE, so you can solve it. So we can see that there are three components. So m is a vector, remember, this is a vector. Magnetization, induced magnetization, is a vector. So this has it will have three components, mx, my, and mz. Okay, and we see that they evolve according to, if you see that mx and my, there is a sinusoidal dependence with respect to time, right? And the frequency, we will see as the frequency depends, this gamma b0 we will see is that is something called the Larmor frequency. I will mention that in the subsequent slides. So from this equation you see that the mx and my components are in this case periodic, right? So which means that there is a precession happening in the xy. So I will illustrate this in the later slides. Okay, so let's look at this. So this, based on this equation, we saw that this omega 0 is gamma b0 is called the Larmor frequency, and as units of radians per second. And of course we can always rewrite this as nu 0 is gamma b0 by 2 pi, and we can rewrite the equations we saw in the previous slides in this form. Okay, so what is this motion? This is similar to that of a top or a gyroscope in a gravitational field, and in this case the axis of the top is the direction of m, basically the direction of the magnetization is same as the axis of the top, and the z-axis is the direction of the which is the direction of the acceleration due to gravity. In this case is the direction of the static magnetic field. Okay, so these two equations refer to means that there is a precession, okay, around z, which is the same as the direction of the b0 field, okay, around the z-axis. So there is a precession of this magnetization in the around the direction of the applied static electric field. Yes, applied static magnetic field. Sorry, I said electric field, was a mistake. So this is just basically these two equations denote a precession around that direction, right? Because you remember, if you look at this, the mx and my are they are kind of periodic, or in this case sinusoidal motion. Okay, so once again, what this Larmor frequency we saw is actually dependent on the ferromagnetic ratio times B0. B0 is the applied static magnetic field. Now, there are three sources of the static magnetic field fluctuations. One is there is inhomogeneity itself, with the hardware itself. You cannot exactly have B0 everywhere spatially. So there are going to be some fluctuations there. There are two other properties, intrinsic properties of the sample, which is the magnetic susceptibility and something called chemical shift. These two affect the value of B0 locally. In the sense we know B0 is a function of R. Let's say if we write this as a function of R and time, we'll exclude time of R. Now we expect this to be B0 everywhere, but there will be some delta B because of these two properties, and actually this is exploited for imaging, right? Because you will see later that because this B0 varies, consequently this omega naught will also be slightly different, and that's what is used for obtaining contrast. Okay. So the groups of nuclei in a spin system that are the same Larmor frequency are called isochromats. So the hydrogen nuclei in water will form an isochromat, while those in fat will form another isochromat, because it might have a slightly different Larmor frequency, because B0 is slightly modified because of the chemical surrounding. Sorry, I used a wiper instead of right here, B0. Okay. All right. Next, so we'll also now look at some nomenclature. Okay, transverse and longitudinal magnetization. Where do these come from, right? So the M, as we saw, has two components. As we can think of them as having two components. One is longitudinal component, which is along the direction of the static magnetic field. Remember, the direction of the static magnetic field we said will be typically along B0. Okay, That is basically B0 direction is also taken as the Z axis. Typically, that's how it is, right? And mx and my, which is we saw, right? There is a equation of motion for mx and my, and there's actually sinusoidal dependence, right? And that component, in plane component as we call it, is we call mxy. Mxy is written in complex form like this, mx plus jy. This actually simplifies a lot of the analysis. That's why they write it. And then there is a direction, which is basically an initial direction, which is tan inverse my by mx, right? This is basically this particular angle, I guess. You can look at it that way. So this alpha I have indicated here. Typically there is a, you would assume that there is some tilt away from the axis and then it's processing around it. So even with just a static magnetization, magnetic field applied, along the z axis, the spins, the individual spins align preferentially along the direction of the static magnetic field, and they also precess around the direction of the static magnetic field. There is an arbitrary phase associated with it. Okay. Now, this is what I was trying to imply from the previous slide. So you can think of individual nuclei, or the protons in this case. These are hydrogen atom protons, right? Because they are the most abundant in the body, and they have this spin property, and the spin is basically think of it as contributing, and in fact that's what gives rise to the magnetic properties of the material. So you can think of it as like some compass pointing along a particular direction, right? That's what is indicated here, and the direction with which it points is the direction of the magnetization induced. You can think of it that way. And when there is no static magnetic field, all these are randomly aligned, leading to a net magnetization of 0. Now, in the presence of a static magnetic field, you would have all of them preferentially aligned along the direction. So the net alignment is along the direction, okay, and which is what is shown here in this figure. You see that most of them are pointing upwards, and therefore if we take a component along the direction of B0 field, there is always a component along the direction of B0 field, okay. And you'll also see that you can say that since they are pointing in arbitrary directions, the transverse component might cancel and become 0. So generally there is only a component pointing along the direction, and there is a precession, right? So which means that if you think of this as a net magnetization, right, and this precesses around the direction of the magnetic field. So that's the general setup for an MR experiment or an MR imaging experiment. So your sample is basically a human patient, or for that matter any other tissue sample or biological sample. It's placed in a static magnetic field pointing along the z axis, and consequently all the magnetic spins or the nuclear magnetic spins are aligned preferentially along the direction of the static magnetic field, and there is a precession also. And this is the initial setup. So then how do we make the measurement? Where does the measurement come from, right? So that's what we want to do. So this is the picture. So this is a precession that I was talking about. So there is a B0 field along the z axis. These are the individual, let's say, magnetic spins, which are in general precessing around the direction of the magnetic field, right? Now, if you think about it, then you can of course do a vector sum and have like one arrow processing. So there will be a component along z, and there is a in plane component, which is the xy plane component, which is like this. If you think one component which will also be processing, okay, in a particular direction. We saw there is an xy component, right? The z direction, there's an mz component which is along this direction, and there is a mxy component here. Okay, so this magnetization, which is rapidly rotating with the frequency mu0, proportional to nu0, in the plane, and if you put like a coil of wire here, right, appropriate coils of wire here, it will induce a current. It will induce a current in this, right, and that current is your the NMR signal. What is the origin of that NMR signal, right? That's what we are looking for. So the XY component, as we saw, when we go back to the previous slide, XY component, we saw mx and my have a sinusoidal dependence, and we can write it in this form, where this mu0 comes, right? This mu0 is the Larmor frequency that we saw, okay? This means that in the plane, as I indicated earlier, the mxy component is rotating rapidly, okay? Now, in there, since there is a rotating magnetization, if we place a coil of wire outside the sample, then this rotating magnetization can be measured. Okay, and this is exactly what is used in an NMR signal. Okay, it is what's used in MR. This is the origin of the NMR signal, right? So this magnetization, let me go back here, signal. Okay, so the signal frequencies in MR, this nu zero, it turns out to be it's in the radio frequency range. Okay, megahertz radio frequency range. And so then the radio waves are generated by the coils, and in fact there is one more step that we'll get to where we actually need to generate a radio wave in order to measure another radio wave frequency. Okay, so there is how do we know, how do we associate a signal we are measuring to this quantity here? That's the important part, right? So we saw that we have a net magnetization because of the static magnetic field. There is a it's precessing around the direction of the static magnetic field. There is a component in plane, one in plane in the sense there is you can split that magnetization into two components, where it's a vector, one component along the direction of the magnetic field, another one perpendicular to it. The one perpendicular to it is what we can measure, okay, and that can be measured by, because it's actually rapidly changing as a function of time. We can place a coil of wire and it will induce a current in it, and that current can be measured. Now we want to now relate the signal that we are measuring, that current induced or voltage induced EMF as it's called, and the magnetization, and that relationship will then help us to map the magnetization across the volume. Okay, so we won't get into the details, but what we can do is we can actually derive an expression for a rapidly rotating magnetization cutting across a coil. Okay, so there is a coil of wire, something like this, multiple coils, and then there is a M field, right? M magnetization, which is rapidly every time it rotates, it cuts across the coil of wires. This will generate a signal in the wire. Okay, now this will involve integrating across the area of the coil. Okay, so you will be measuring a net magnetization, and you will have to integrate across the area of the coil. Now this is a problem. Okay, so just give you a qualitative reasoning. See, measuring net magnetization is pointless, right? Because what we want is spatial localization, right? That's what an image is, right? Remember, for CT images we were able to localize density differences, right? Because when you reconstruct, the signal is proportional to the density. This mu is a function of energy. The linear attenuation coefficient that we reconstructed is actually a function of the energy as well as the density of the object, the atomic number. So similarly, the net, if we do this particular analysis, wherein we keep a coil of wire, and if you do the analysis like you integrate across the area of the coil, that is typically what you would do, because if you want to calculate the flux, you'd end up doing that. But that doesn't help, because you will be only able to measure one quantity, which is the net magnetization. What we want is magnetization as a function of R time, where R is in the sample, let's say the human body. On every position we want to be able to localize, right? So there is something called the principle of reciprocity, which lets you rewrite that integral in terms of a volume integral of M. Okay, so the rate of the change of the flux, which is the derivative of the flux across the coil, that can be rewritten as a volumetric integral of the magnetization. Okay, and that is called the principle of reciprocity. Once again, this is just for qualitative understanding. You don't have to get into the details. I'll just show you the expression that is involved, and in the end, what is more important is, yes, I have to understand what the MR signal that one is measuring, what is it proportional to, right? What influences that signal? That's what we're heading towards. Qualitatively understand that part. Okay, so if you look at this, for the MXY, is proportional to this. This is the signal we have. We saw that, right? We solved that ODE. If you solve the ODE for the magnetization or the angular momentum, then you get expressions for MX and NY, which were sinusoidal dependence. Okay, so you can put them together as MXY, right, in complex form, and the induced voltage in the coil of wire can be written in this form, where M is the magnetization. So this is a vector dot product, so both of them things are vector, and BR is the this is the magnetic field produced by the receive coil, the coil that you're using to measure It's called the receive coil, and this is the magnetic field produced by the receive coil at a position or the same position R due to a unit current. Once again, we won't go into the details of this derivation. I will just to give you an idea of how we are going to proceed with the analysis, right? So it turns out then after we can actually make some simplifying assumptions, and in the end, if you look at the magnitude of the voltage induced, magnitude of the signal induced, it is proportional to this nu zero, which is the return is the Larmor frequency. This is what you call the voxel volume. In this case, it's an infinitesimal volume. Okay, you think of this as a volume over which the magnetic field is constant, static magnetic field is constant, or M is constant. M0, which is the induced magnetization, the magnitude, right, and sine alpha. Sine alpha is the tilt from the axis, right? Remember, we showed this picture. This is the z axis, and this is the induced magnetization, and it's at an angle alpha. Okay, so this can be maximized. So it depends on all of this. So if you have very high M0, the signal is very high. If nu 0 is high, signal is very high. Alpha is high. Maximum alpha is pi over 2. Okay. So if alpha is pi over 2, which means that you flip the and magnetization is actually in the plane, in this direction, then your signal is very high. So the next step is, in order to get a good signal, what is done is to tip this magnetization, which is now processing around the direction of the static magnetic field, tip it into the plane, which is perpendicular to the plane perpendicular to the direction of the static magnetic field. So that is that is how you would actually induce the MR signal that you typically get in all these imaging experiments. Okay. So there is one other concept you will come across. I will just briefly touch upon it. It's called the rotating frame of reference, right? So if you look, if you tip, let's say the MXY component is in the plane, right? It is processing at a frequency nu 0. This is a very high frequency, okay, radio frequency range. On the other hand, you can actually let the coordinate system rotate at this frequency. If you get the coordinate system rotate at this frequency, then your magnetization is basically it's not moving, right? Or it's not rotating or anything. It is just some vector with this magnitude, stationary vector with a magnitude and a phase angle. That's all it reduces to. Okay. So this is the idea. So but this actually simplifies analysis quite a bit. So that's why people use rotating frames of reference when you're working on analyzing MR signals. So in order to generate like a good MR signal, we have to tip this magnetization vector. We saw M into the plane. We saw that, right? It's proportional to sine alpha. Alpha is pi by 2 is maximum. So you make it 9. So you flip it into the tip that magnetization into the plane. You get very good signal. How do you tip this magnetization? This is where this nuclear magnetic resonance aspect comes in. Okay. So the way the tipping is done is by applying an RF signal. So the energy for tipping the magnetization into the plane is provided by a RF signal. So there is another coil which generates a magnetic field. It's called the B1 field. I have not mentioned it here. And this B1 field incidentally also is oscillating at the Larmor frequency. Why do we need that? If you think about it, let's say you apply the B1 field at an arbitrary frequency, but its B1 field is always perpendicular to the B0 field. If B0 is along Z axis, B1 let's say will be along the X. This is the B1 field. Now what happened? We saw, right? So we saw that M cross B, the torque is M cross B. So when you apply this B1, this will also produce a torque. However, the B0 field is always much stronger. This B1 field is much lesser than B0 field, so it won't be able to to influence that magnetization that much, because the B0 field will eventually also have a torque on it. It becomes an issue. So the way to do that is by doing something in resonance, which is basically applying this rapidly oscillating B0 field, which oscillates at the same frequency B of nu 0. Okay. The idea is, if the B1 field also oscillates, then it will rapidly push the magnetization into the plane. Okay, so that's where the resonance aspect comes. The resonance is called resonance imaging because the applied B1 field, which you applied at right angles to the B0 field, will put a torque on it, which will force the magnetization into the plane. But however, it will not be enough, right? Because the B0 field is always stronger. Okay. So then you have to do it at a certain frequency nu 0. This oscillating field has to be at frequency nu 0 in order for it to tip. Okay. And the tip angle is generally given by this expression 0 to, it depends on how much time you apply. So the B1 field is not permanent like the B0 field. You apply it for a specific period of time. That period of time determines how much, by what angle you tip the magnetization, and it is given by this integral expression. Okay. Again, this gamma will be there as a prefix. Alright. So what's essentially happening is, if you look at it in the rotating frame of reference, this is your net magnetization. Let's say initially it's along Z, just for the sake of argument, for illustration, it's along Z. And again, I use X prime, Y prime, Z prime, it doesn't matter there. It just, I may just mean X, Y, Z. Okay. So it's along Z, and then you apply this B1 field. Remember, let's say I applied it along B1, then it will tip the magnetization into the plane, which is into this plane. Okay. On the other hand, or depending on the duration, right? If you want to tip into the plane, you have to apply it for a proportional period of time. But if you look at it from the laboratory frame of reference, what you are doing is it's actually spiraling. The M is actually spiraling into the plane. Okay, the magnetization is spiraling into the plane. If you look at it in the rotating frame of reference, then it's actually it's just tipping into the plane. Okay. Now, if from the laboratory frame of reference, you can understand this, right? It is spiraling because the applied B1 field also has the same frequency as the precession frequency of the M. Okay, it is just like when you are swing, right? You are somebody on a swing. You have to time your push properly so that next time they go back and forth, they get a higher displacement. It's very similar to that. Okay, so now so this is where the actual imaging signals start to arise. Correct. So once you have tipped it into the plane, what then? Okay, so once the magnetization is tipped, you would think, right? Once you magnetization tipped, you will turn off the B1 field. B1 field is set to 0. Okay. So ideally, if you leave it that way, it should persist there forever. Correct? Because initially you had applied a static magnetic field and they were precessing around the direction of the magnetic field. Now, if you tip it, then you should have a signal there for it. Doesn't happen, unfortunately, because there are physical laws and processes at play. Okay. So these physical processes dampen that motion, that precession in the plane. And so eventually the in plane, the one that the magnetization you tipped in plane will decay. Okay. So there are two processes that lead to that decay. So one of them is called the transverse relaxation or spin-spin relaxation. Okay. And this causes signal to decay, and because of the perturbations in the magnetic field caused by the spins themselves. So neighboring spins will modify the B0 field in the at a particular spin location. Okay. So then this leading to inhomogeneities. Okay. And the way you think of it is dephasing is, if you think of a bunch of spins processing around the in plane, and each of those spins will cause some inhomogeneity somewhere else, right? And that means that the magnetic field there is either reduced or increased, and subsequently the spins at that location will get either a higher frequency or a lower frequency, leading to dephasing. Okay. Only if they are all processing in phase do you get you get a strong signal. Otherwise, the signal goes to 0. Okay. Now the process, once you have tipped, it starts going to 0, but still you can get an induced signal, and that signal is called free induction decay. Right. So the magnetization is tipped into the plane and it's rapidly precessing. This leads to a current or a voltage that can be measured in a coil, and that voltage starts to that signal goes to 0 rapidly because the transverse component will decay. Okay, will decay because of the so-called transverse relaxation process or spin-spin relaxation. Okay, so this is what I have shown here in this particular illustration. So you have a bunch of spins processing around the direction of static magnetic field. You apply this 90-degree RF pulse, which is basically your B1 field, and you tip the spin, you tip the magnetization into the plane. Okay, but as soon as it's tipped, it will start to dephase. So the individual spins will start to all process with different frequencies and getting different directions, and over time they will all there will be so many, all of them will acquire independent precession frequencies and phases, leading to 0 magnetization. Okay, however, this can be measured as a signal. This process can be measured as signal, which will rapidly decay to 0. Okay, and that's called the FID, free induction decay. All right. Mention that this process is actually characterized by the time constant T2. process is time constant T2. So this is where the T2 contrast comes from. Okay. The second, before we go any further, I just want to. The other form of relaxation is the longitudinal relaxation, which is basically the reappearance of the longitudinal magnet. Right? You have the MZ component, right? Now we have tipped it, so then immediately after tipping, MZ will go to 0, but then over time it will slowly start to reappear. Okay. So, but then that process again, this is may not be very obvious at this time, or not very intuitive. The rate at which MXY goes to 0 and the rate at which MZ reappear are different. Okay, so they have different time constants. So that one is T2. This time constant is given by T1. Okay, and for different types of tissue, the T1 and T2 have different ranges. So T1 is always higher. T1 ranges from 250 to 2500 milliseconds, while T2 ranges from 25 to 250. So just to remember, for the sake of understanding, T2 is the time constant which determines how fast your transverse magnetization, which you have tipped into the plane, how fast that goes to 0, because this is the time constant for the processes that drive that component to 0. However, that doesn't mean that you recover the magnetization along the z-axis or along the direction of the static magnetic field instantaneously. That takes a slightly longer time, and that time constant is T1. So this T1 and T2 or those time constants, they depend on the properties of the isochromats. Okay, where are they? I mean, in a sense, what kind of tissue you are imaging, what kind of atom or nuclei you are imaging, right? So in this case, in the body, it's just hydrogen proton, that's a nuclei you are imaging, but then its chemical environment will determine the T1 and T2. Okay. So for all this put together, remember we wrote this equation, this kind of M cross B equal to dJ by dt is something we wrote for, just a magnetization in a static magnetic field. Now if we take into account, there is actually a bracket I left out here, sorry, this is a bracket here, right there, yes. Now if you take into account all these factors that we talked about, and we also include B0 and B1, right? So then we can write down the equations of motion. These are called the block equations in this fashion. So these are two differential equations that show how Mx and My evolve in the presence of in the presence, these equations in the presence of B0 and B1, and this is after B1 is removed. How does it behave? That this determine after B1 is removed, that's when we start the imaging process, correct? And these equations then determine your source of contrast, what your signal depends on, etc. So these are used to actually figure out different types of imaging tricks. They're called sequences in magnetic resonance imaging. Okay. All right. So the first sequence that we are going to talk about, again, this is just for the sake of understanding what exactly is happening. This is called a sequence, an imaging sequence, which is basically what we are trying to do is manipulate this magnetization M. Right. One way we saw how to manipulate this, we tipped it into the plane. That's when we have the coils there that measure the induced signal, and we use that signal to infer the magnetization as a function of position. Okay, and this is what we want to do. And so one of the ways of doing that is this spin echo. Okay, we'll look at the actual 3D imaging sequences in the next video. But this is just for the understanding of how the spin echoes are done. Okay, the spin echo, so we saw that you apply this 90-degree RF pulse, B1 field in this, they're along x-axis. I think maybe I should have done the x differently, but anyway, just for the sake of argument, we'll just do it this way. You apply the B1 field perpendicular to the direction of the magnetic field along one of these axes, and then it will tip. Let's say you do a 90-degree pulse. Okay, I call it the 90-degree pulse. It will tip the RF pulse, which is the B1 field, will tip the magnetization into the plane. However, you can always call it as alpha pulse. The alpha is any angle that you want to tip it. Okay, so the 90-degree pulse will tip it in magnetization into the plane. The red arrow is the magnetization. It will rapidly dephase. Okay, but then now what you do is you apply a 180-degree pulse. So this 180-degree pulse, what it will do is it will flip the magnetization, right? It will flip the magnetization into this way. It's a 180-degree flip from where it is. So what happens is they are still precessing in the same direction. So they will once again come together. here, and that gives rise to another signal, okay, and then followed by a decay. So this one will be a decaying signal because you tipped it immediately and then it starts to dephase, that gives rise to this signal. And what you do is you wait up to a time called TE over 2, it's called the time to echo, and after that, and you apply 180 degree plus. So 90 degree pulse, just to understand, 90 degree plus will flip the magnetization by 90 degrees. 180 degree plus will flip the magnetization by 180 degrees. In this case, when you flip by 180 degrees, you actually go right over there, you flip around, you can flip around the y-axis here according to this picture, but then you are still processing in the same direction, you are all processing in different directions, right? So then you will come together once again to form another and gives rise to another signal. So that's what is shown here, right? So you go once you get this other signal, it's rising because you come together and then you will decay again. So this is the spin echo, okay, and the 180 degree pulse is applied at time t from t by 2 from the time you applied the 90 degree pulse, and then you will measure the echo at time te, okay. So time to echo. So this is one parameter that people manipulate all the time to echo, okay. When you measure the signal te, okay, will determine your contrast. We will see that in the later slides. To determine the contrast. There's one more time which is called TR, that's called the repetition time. So for instance, in all of these experiments, it's not like you just do this once and then that's it, you're done. No, you will have to do these sequences in order several times. The time between each time and the time between each of these, very crudely speaking, the time between each of these 90 degree pulses. Every time you have to apply 90 degree plus to flip the magnetization in plane. So which, and that time between two successive these 90 degree pulses, you can call it time to repetition, okay. So this T and TR determine contrast, okay. So we will see that how that happens. So there are different forms of contrast. We saw that earlier also, I mentioned it, T1, T2 and PD. We will see how that is, okay. So the basic contrast mechanisms, right, the type and ordering of excitations and relative timing, that leads to different type of tissue contrasts, okay. And this is what is specified using a pulse sequence, okay, all right. So this pulse sequence determines what kind of contrast you are getting, okay. The time interval, like I said, between two successive alpha pulses is the time to repetition. We saw what is the time to echo, the last slide, okay. See, only the transverse magnetization provides the measurable signal, okay. So larger the transverse component, higher the signal, okay. And if you want to see contrast in different types of tissue, the measured signal must be different in these tissues, right? That's how you do, right? The magnetization that you measure in these different tissue types should be different, because we saw that the signal magnitude of V, remember that expression last a few slides ago, it depends on M0. So whether if M0 is different, then you get good contrast. If they are the same, you don't get contrast, okay? So the contrast is provided by three main properties. We saw proton density. Proton density, understandable, right? Because if there are more protons, you get a bigger M0, right? Because each of those protons contributes to the net magnetization. And there is the T1 and T2 weighted time. So we saw what T1 was. T1 was the rate at which you recover the longitudinal magnetization, okay? And that is a tissue dependent property, okay? It depends on the chemical or the biochemical constitution of that particular tissue. And T2 also same thing, it is a chemical property, right? Because you are looking at how fast does the fins dephase in the plane, and that depends on the kind of inhomogeneities introduced by other spins in there, and that depends once again on the chemical composition of the tissue at hand. So both of these are tissue dependent, these properties, and we can capture these properties by playing with TR and TE. There's other property is TE. How soon you measure. Alright, so proton density weighted imaging, and this is accomplished by long TR and either no echo or short TE, right? Why do we do that? See, if you wait long enough, right? So long TR is between two successive pulse sequences, that is the time TR. So before you apply the second pulse, you wait for the longitudinal magnetization to recover completely. Now, different tissue will have different T1 times, which means that the amount of magnetization that is recovered for different tissues will be, let's say there are two different types of tissue, right? I'll do red and blue and let's say green, This blue and red. This one is T. This, let's say this is 100 milliseconds or 1000 milliseconds. This is 2000 milliseconds, right? This is T1. Let's say it's T2 is, this is 20 milliseconds. This is milliseconds, and this is 40, or in this case 5 milliseconds. Okay. So the idea is, if we wait long enough, we don't wait long enough. Let's say we start the second experiment, second pulse, alpha pulse, at immediately at the first alpha pulse at time 0, second alpha pulse, let's say we apply at 1000 milliseconds, right? Then what happens is that in this tissue, the longitudinal magnetization has not recovered, correct? Longitudinal magnetization has not recovered here, but it has recovered there. So consequently, the M0 that we measure will be higher from this tissue compared to that, right? Similarly, for the T2 time, T2 determines how fast it goes to 0. Okay, so if you measure soon, if your time to echo is very short, is only what, let's say in this case, let's say it's only 5 milliseconds, right? You won't be able to capture this one, right? This signal, because this is dissipated by that time. Let's say you are measuring time to echo as 5 milliseconds, then all of this, the contribution from this tissue would have dissipated by 5 milliseconds. Why you will only get the 20 millisecond component, right? So the idea is, we don't want that to happen. We want it to strictly depend on the density of the protons in each of them. So what you do, you wait long enough. Let's say you wait 5000 milliseconds, which means that the longitudinal magnetization would have recovered in both of these tissue sets, right? And then once you flip, you measure immediately, which means that you don't, these T2 times will not influence your measurement, right? So that's how you get proton density weighted imaging. So like I said, T2 weighted contrast, difference in T2 relaxation times must be apparent, okay? So which means that T must be selected to be T2 value of the image of the tissue being imaged, and we should have large TR to reduce T1 effects, right? So we need a large TR so that the T1 factor is not shown. So all the magnetization in all the tissue will recover large TR. But if you want to have just want to get T2, then you just measure at some, at the tissue, for instance, should be approximately selected to be T2 of the tissue being imaged. So you can either choose, let's say you want at T2, see if you wait too long, all of them will go to 0, right? If you wait too long to measure, all of these will dephase. Let's say 5 milliseconds and 20 milliseconds. If you wait 40 milliseconds, the spins from both of them would have gone to 0. So you won't be able to, would have gone to almost close to 0 or be very low. You won't be able to make the difference. So you want to measure this tissue, means you take the time to echo as 5 milliseconds and measure that. Okay. T1 weighted contrast, same thing. Where you make sure TR must be set approximately close to T1. So in this case, if you want to measure this tissue, you set TR to 1000, which means that only that tissue would have recovered. So you will get a high signal from there. Okay. So that's the idea behind how you get different types of contrast. Okay. So you have to think about it a bit. So understand that T1 is the time constant for the recovery of longitudinal magnetization. T2 is the time constant for the dissipation of the transverse magnetization. Remember that the transverse magnetization is what gives rise to the signal, and the transverse magnetization is actually from the longitudinal magnetization, because that's what you tip into the plane. Okay, so the larger your longitudinal magnetization, the higher your transverse after the application of the RF pulse. Okay, so that's all for this class. So the understanding here, okay, just to summarize, the idea is you have all these protons in our body from the hydrogen atom nucleus. They all have a spin angular momentum property which can interact with the static magnetic field, very high value static magnetic field, and which leads to a net magnetization. This magnetization precesses around the direction of the static magnetic field with a certain characteristic frequency called the Larmor frequency, which is mu 0 or nu 0. Then upon the application of another or rapidly oscillating magnetic field, and I say rapidly oscillating, I mean it is the same frequency as the Larmor frequency that you are trying to of the material you are trying to measure. So upon the application of that, the precessing magnetization is tipped into the plane. Okay, we call that the transverse magnetization, and once again it's still processing at the alarm frequency, giving rise to a signal in a coil of wire. Okay, and there are these three important factors that determine the strength of the signal, which are basically the T1 relaxation time, T2 relaxation time, and proton density. By appropriately tuning your time to repetition, which is the time between two successive alpha pulses, and the time to echo. Time to echo is the time from the application of the alpha pulse to the measurement of the signal in your coil of wire. By changing those times, you can make sure that either the proton density is what contributes mostly to the image contrast, or it's only the T2 times. The difference in T2 relaxation times is what contributes to the contrast, or the difference in T1 relaxation times. Okay. Once again, before I conclude, I would make that point that these are relative, right? So when we say T1 relaxation time, you are not going to be able to absolutely measure 1000 millisecond from the voxel values. So if something has a, for instance, of just as a example, if some part of the tissue has a higher relaxation time, maybe depending on the TR, it will appear dark. The lower relaxation time, T1 relaxation time, might appear bright. Okay. Similarly for TE, now if you, depending on how soon you do these measurements, right, the lower TE might appear darker, higher TE might appear brighter. Okay. So this is why, and of course proton density, once again, is also relative. The higher, you can only see relative contrast, in the sense something is darker means there's either more or less protons than the other regions. Okay. So this, but then if you look, this kind of gives you the flexibility to do multiple different contrast mechanisms. That's why MR is one of the kind of highly researched imaging modality, because the modes of contrast are huge. I only talked about two or three different. These are the most commonly done, but there are other contrast mechanisms also that can be done, and that is a lot of interesting research going on in that area. Okay, thank you. That's all for this class.